Hi everybody, let's have a discussion today of covalent bonds. So when we're thinking about a covalent bond, remember this happens because we are able to decrease the potential energy for atoms. And remember, potential energy for atoms is like stress. They really don't want a high potential energy because that's a stressful state for them to be in. And so they can do this by essentially completing their octets or getting rid of electrons to form octets. Let's see how that looks a little bit more closely. So remember, we have atoms coming together. They're looking to bond so they can decrease the potential energy. And what happens is we have charged nuclei, right? These are positively charged, and then we have negatively charged electrons. So the positive charge from one atom, let's say this one on the left, is attracted to the negative electrons in this atom, and vice versa. And eventually they get to a kind of a place where they're really happy in this bond. But the question is, how far apart is that? And so if you think about these atoms approaching one another, we can look at this graphically. And if you look at this graph, we'll start over here at letter A with the atoms far apart. And on the y-axis here, we're looking at potential energy. So high potential energy, again, is bad. Low potential energy, so down here, would be good. At letter A, we have a very high potential energy. We're up here. Those atoms are really far apart. They're really not associated with one another, right? There's nothing going on there. But as we get over here to letter B, gradually that negative charge from those electrons of one atom starts to be attracted to the positive charge of the nucleus of another electron. And so that's starting to become a state where the atoms are a little bit less stressed out. They have a lower potential energy. You can see this red line is getting lower as we go along. And eventually, whenever we hit point C, notice how quickly the potential energy line drops. So at point C, there's a distance apart that's really good for these atoms. It turns out for these two atoms, it is 75 picometers. Right at that point is the point at which we've minimized our potential energy. And at minimum potential energy, that is when the atoms are most stable and they're most happy with their full octets. So there's a distance, this length, there's a happy medium for all combinations of atoms, right? And that is referred to as their bond length. And it's different for different atoms depending on what is bonded together, but it always is at the trough of this potential energy graph, and it is the distance between nuclei. And then eventually, as you get over here to letter D, we get to a point where those nuclei get too close. And because both nuclei are positive, remember two positive charges are going to repel, they repel one another, we start getting a really stressful state again, right? They're getting too close to one another, they don't like this, so you notice the potential energy jumps way back up. It turns out that there is a relationship between bond length and bond strength. And so another way of talking about bond strength is bond energy. And so when we talk about when we talk about bond length, that's the distance between two nuclei, again, at that lowest potential energy, the minimum potential energy. But bond energy, or bond strength, is how much energy you need to break a bond. So the more energy you need to break a bond, the stronger the bond, right? If you need very little energy to break it, it was a very weak bond to begin with. And it turns out that these two are inversely related. So long bonds tend to be rather weak, whereas short bonds tend to be rather strong. And we've given you, on your note guide, where I'm going to join you, we've given you kind of this nice table. And on the table, you'll notice that we have bond lengths, and we also have bond energy. And remember, bond energy, the higher that number, the stronger the bond. And as you look down these columns, you'll notice that in general, there's an inverse relationship between energy and length. So stronger bonds are shorter, and weaker bonds are longer. So as we look down to number one, what is the relationship between bond energy and bond length? Well, this is an inverse relationship. And it allows us to do some things, especially if we have the data like you see in that table. It allows us to go through and identify some different trends. So for instance, number two, we're asked to arrange these in increasing bond strength. And remember, bond strength, another word for that is bond energy. The higher the numbers in this table up here, the stronger the bond, because it takes more energy to break. So let's identify the numbers from that table for these four types of bonds. CCl has a bond energy of 397. CI has a bond energy of 209. HF is 570. And II is 151. II, just so you know, is a pirate's favorite type of bond. You can laugh now if you'd like. All right, moving on. So our goal is to order these in increasing bond strength. So if we're asked to order something in a fashion that is increasing, that means getting from smallest to largest. So we're going to take our smallest number. That was the II bond. Again, that pirate's favorite type of molecule there. Next up was 209, which is Ci. Next up was CCl because it's at 397, and finally our 570 is HF. So that goes from the weakest bond to break to the strongest bond between H and F. So again, as you're looking at the table and you're asked which is the strongest bond, well, we've just talked about that. That is our HF bond. It is the strongest, it's the highest value on the whole table. That's the strongest. And conversely, the weakest bond, this one is that old II bond, right? It has the lowest bond energy. It takes the least amount of energy to break. Therefore, it was the weakest to begin with. Let's do it as well, but let's now talk about strength, and let's talk about strength as it relates to length. Remember, there's an inverse relationship between bond strength and bond length. So if we're going to arrange things in order of increasing bond strength, that means going from weakest to strongest, then we want to start with the longest bonds because the longest bonds are the weakest bonds. And so the longest bond we see here is this 398 picometer bond. Relative to the others, it's long, followed by the 149, followed by 72, which is followed by 53 because that is the shortest bond, and we know because there's an inverse relationship, the shortest is the strongest. Now for number 5, you have a really nice periodic table on your note guide. It's located right here. You might want to do some work there. I'm going to jump over to another periodic table just to illustrate a little trend that you probably could already predict. But here's our electronegativity periodic table. We don't need the electronegativities. I'm just using this to see the different elements in their different columns. So as a reminder, we've already talked about the S and P sublevels. So everything in the first column, and I've numbered them here, here's number 1, everything here would end its electron configuration with S1. Everything here would be S2. Everything here would be P1 all the way up to P6. And as a reminder, the S and P sublevels are our valence electrons. So if we wanted to count up the number of valence electrons for these atoms, what we can do is look at how many S and P electrons they have. And remember, we're only in the outermost energy level. So lithium is in this first column. It only has an S1 electron. Therefore, lithium has 1 valence electron. Let me make that pink to match with lithium. So lithium has 1 valence electron. Carbon, meanwhile, has 2 S's, right? Because it took these 2, and it has 2 P's. So if you put those 4 together, or those 2 and 2 together, you get 4. So carbon has 4 valence electrons. Sulfur has, again, the 2 S's, but it has 4 P's. So it has 6 valence electrons. And neon has the 2 S's plus 6 P's, therefore it has a grand total of 8 valence electrons. It's already got its full octet. That describes why it's a noble gas, why it doesn't bond, why it doesn't want to gain or lose electrons. And so really, as we're talking about valence electrons, there's a trend that you probably already realized, which is that if you just look at the column number, which I've identified up here, so column number 1, 2, and then we're going to skip the middle part. We're just going to skip the middle. And then we go over to 3, 4, 5, 6, 7, 8. That column number is equal to the number of valence electrons for each type of atom. And that's going to be really useful for us later on in this unit. So make sure you can do, for elements in the leftmost 2 columns and the rightmost 6 columns, can you identify how many valence electrons they have? And again, it's just equal to their column number as we skip the middle. And if you remember, for those of you who are really into electron configurations, remember whenever we went into the middle part, we went into the D sublevel. So for instance, this energy level says 4s2, 3d10, 4p6. That's that entire row. And so this helps to illustrate why the middle can be skipped, because you'll notice it's an energy level down. It's in the 3rd energy level. It's not the valence level. So when we're counting valence electrons, we would count these 4 and these 6, which is why we can just ignore this whole middle section.